Hello again, Math 210 class. Um, Today we're going to get into section 8.1. However, before we do that, I just want to put a pin in something from chapter 7. It's something I found helpful to kind of organize my thoughts when deciding which method to use to find the volume of a solid of revolution. So here you see I have kind of a table set up. If we have a horizontal axis of revolution or a vertical one, if the function and limits of integration are in terms of the variable x versus being in terms of the variable y, we can kind of fill this in. So let's see here. If we have a horizontal axis and everything is in terms of x, that's actually going to require disk washer method. And so now that you see like kind of what's going on here, if you want, pause the video and see if you can fill the rest of these in. But we'll just continue with that for now. Now, if everything is still in terms of x, but I'm rotating about a vertical axis, then we saw in section 7.3 that we need what's known as shell method, right? And now here, if everything is in terms of y, and I'm rotating about a vertical axis, that is section 7.2, that's disk washer. And now, process of elimination. But here, you'll notice that we have a horizontal axis and function and limits of integration in terms of y. That's also going to be shell method. So hopefully this helps organize your thoughts moving forward. But that's just something I always found helpful. Okay, let's get into chapter 8 now. Okay, so we're going to start off by looking at what are known as sequences. And first and foremost, a sequence, this is probably the most important definition of a sequence, is just that it's just a list of numbers. So what's nice about sequences is often you're given a rule to how to find each what's known as element or item or term of a sequence. So here, what this notation tells us, if I start with n equals 1, I get 1 over 2. And now what you do is you just make a list. So you put a comma, and now plug in the next integer after this, so 2, and I get 2 over 3. And then next, plug in the next integer, 3 over 4, 4 over 5, and so on, right? And that's what this infinity means here. It just means, keep going for every integer after 1, including 1. So that was an easy first example. Now this next one here, things get a little bit more complicated. Notice that we're going to start with 0. So let's see. The first denominator, I think that's the easier thing to do here. You just get 3 to the 0, which is 1, right? Maybe I'll write it as 3 to the 0. And now here I get minus 1 to the 0. Use parentheses, right? And then here I get 0 plus 1. Well, that's times 1, okay? And now plug in 1. That's the next integer after 0. So I get minus 1 to the 1 times 2 all over 3 to the first, right? And then the next one will be minus 1 squared. And then we get a 3 here. Remember, n is 2, so 2 plus 1 is 3. And then over 3 squared. And so on. And we use these curly braces to enclose the sequence. And now let's simplify this. So the first entry here, the first term of the sequence, well, any number to the 0 power is just 1 times 1. I get 1 on the top. 3 to the 0 is 1, so I get 1 on the bottom. Next one here, negative 1 to the first is negative, and then I get a 2 over 3. Now this one here, you'll notice I'm squaring a negative, so that's actually positive 1 times 3 is 3 over 9, which is actually 1/3, right? 3 over 9, 1/3. The next one will be minus 4 over, let's see, 3 cubed, which is 27, and so on. And so this is our first example of what's known as an alternating sequence. And hopefully it's clear why. With every term, it switches from positive to negative, and then back to positive, then back to negative, and so on and so forth. Okay. All right, so for this next one, we start with 3, so I get the square root of 0, which we can do. Then I plug in 4, and I get the square root of 1. And then plug in 5, I get the square root of 2. Plug in 6, square root of 3, then square root of 4, and so on. And I'm just going to simplify this. Square root of 0 is 0. Square root of 1 is 1. The next 2 I can't simplify, but the square root of 4 I know is 2. The next term would be square root of 5, and so on and so forth. Okay, and now here, well, this is start with 0, so I get cosine of, well, 0 pi over 6, which is just cosine of 0. Then plug in 1, so I get cosine pi over 6. Then cosine 2 pi over 6, which is pi over 3. Cosine 3 pi over 6, which is pi over 2. And we'll just say so on and so forth from there. Cosine of 0 is 1. Cosine pi over 6 is square root of 3 over 2. Cosine pi over 3 is 1/2. Cosine pi over 2 is 0, and so on and so forth. Okay, so now let's kind of work backwards. So you see, in the last example, we had a rule for finding each term of the sequence. And now this example, you're going to be given a sequence and asked to find the rule. So it actually depends on where you start. So let's just say for both of these, we want to start with n greater than or equal to 1. So we're going to start with n equals 1 and then go from there. And we'll call the nth term an. That's just general notation there. Well, it looks like each term is a fraction. And on the bottom, it looks like we're getting a power of 5. This is 5 to the first, 5 squared, 5 cubed, and so on. So since I'm starting with n equals 1, I think the bottom here is just 5 to the n. Now you'll notice I have an alternating sequence. It starts positive, then negative, and so on and so on. And now I'm starting with 1, so I can't just have n here, because negative 1 to the first would be a negative number, but I'm supposed to get a positive. So the way you get around that is you just add 1 to it. And now when n is 1, n plus 1 is 2, and so I get minus 1 squared, which is a positive to start off with. And now you'll notice in the numerator, I'm always getting 2 more than my index, which I guess is n in this case. So I think it's going to be like n plus 2, right? And then just make sure, like, I don't know, if n is 3, then I get negative 1 to the fourth, which is just positive 1. 3 plus 2 is 5. Over 5 cubed is 125. So that, it works. Okay, so go ahead and maybe try the same thing here. Pause the video, but I'll just go ahead and do it. Once again, we have a fraction. It looks like if we're going to start with n equal to 1 and use bigger numbers, integers than that, then it looks like the bottom is always just n plus 1. It's alternating again. So I could use, let's see, does negative 1 to the n work? Well, no, n is starting with 1, so it needs to be n plus 1. Or equivalently, you could use n minus 1. That also works. So I'll leave it up to you. You could put plus 1 or minus 1. It doesn't really matter. And now the numerator, like the actual number up here, it looks like all of those are perfect squares, starting with 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So I think this is times n squared. Now everyone's favorite sequence is the Fibonacci sequence. So I figured I'd just throw this in here for you. The first 2 terms are 1 and 1. And then to get any other term, you just add the previous 2. So the next term would be 2. And then to get the next term, it's 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8, etc. Next one would be 13, so on and so forth. It turns out that there is actually a rule for this, much like something like this, but it's a little bit harder to find. It's outside the scope of the course. Okay, so let's go back to our very first example, this n over n plus 1. Here's the sequence for you. And here's actually a visual representation of it. You can actually graph it, right? Like if the horizontal axis, let's say, is n, that's our index, then just plot the corresponding height as the term. So here, when n is 1, I get 1/2. When n is 2, I get 2/3, then 3/4, 4/5, etc. And what we're seeing, it looks like these terms are sort of leveling off towards a value of 1, which we're going to call the limit, right? So this is just an interesting way to verify that, but we're going to get to an easier way in just a second. You'll notice here I cleverly add 0. If you had me in Calc 1, you know, cleverly adding 0 or multiplying by 1 is a typical strategy in math. And then if I associate these two, n plus 1 over n plus 1 is just 1, and then minus 1 over n plus 1. So this is another way to look at this same sequence. And now as n becomes large, 1 over n plus 1 is very small, and so you just get 1 as the limit, which makes sense looking at the picture of the sequence. Okay, so we just like with functions, we have this notion of convergence, and I like to say that a sequence converges if the terms of the sequence settle down, I guess I'll say. And so go ahead and read this, this next example and remark. But really, this theorem is the heart of the matter here. So let's say I wanted to find the limit n goes to infinity n over n plus 1. Can I show that this is 1 by more conventional Calc 1 methods? Well, think about this in your mind. If I just replaced n by x, then I should be able to compute this. Notice I get infinity over infinity, so maybe I throw L'Hopital's rule at this, and I get limit x goes to infinity. Well, it'll be 1 over 1, which is 1, right? Well, what this theorem here says, it says that if you can do this, then you're allowed to do it, right? So like here, if I think of these n's as x's, then I can just use L'Hopital's rule, and just by Calc 1 methods, I just get the limit is equal to 1, right? Okay, but there is a limitation to this. Of course there is. So I think the second example we had above was an equals minus 1 to the n plus 1 times n plus 2 all over 5 to the n. Well, if you try to take a limit of this by like thinking of the n's as x's, what you would get is something like this. And most of this is all right, but right here, there's maybe alarm bells going off. If x is not an integer, minus 1, like let's say if x is 1/2, minus 1 to the 1.5 is not a real number. Like you have to use complex numbers in order to find that. So you can't really compute it using conventional methods. So anytime you have something like this alternating, and there are other examples out there with factorials and so forth, you have to use different methods. But for now, if there is no alternating part, if it just looks like a normal function, but with n's instead of x's, then you can just use your usual Calc 1 methods to find the limit. And so we have, of course, notation. If you can take the limit and get a number, we say that it's convergent. And if you can't take the limit or you get like an infinite value, then we say that the value diverges, or the sequence diverges. So now, looking at this fact here, rules of convergent sequences, I want to highlight here. In order for these bullet marks here to be true, each sequence has to first converge, okay? So both of the sequences individually need to converge to some number. Then you can do exactly what you think you should be able to do. If you add the two sequences, it's just the limits added together. If you subtract them, it's the individual limits subtracted, so on and so forth. Okay. And then finally on this page, and this will be the end of the video here, let's talk about squeeze theorem. So we had this in Calc 1. It's the same idea here. So let's suppose that we have two nice sequences that limit to, let's say, some value L. Okay. Then let's say now we have a new sequence in green that eventually squeezes its way in between the two sequences. So at the beginning it can be a little erratic, but eventually it finds its way in between the two sequences. Then because the blue sequence and the black sequence converge to the same value, this green one is going to converge to the same value, L, as well, right? And that's all that this is saying. Okay, that's the end of this video. In the next video, we'll continue with section 8.1 notes.